Swayam Prabha. Digital India. Educated India.
Welcome back, learners. The video is for the subject of Geography for the course of Bachelor's in Arts with Geography or Bachelor's in Arts with Honours in Geography. The video is for the paper of Climatology. Today we will be starting with Module 4 of Climatology, which is Humidity and Precipitation. The Lecture 1 topic of Module 4 is Humidity, Atmospheric Stability and Instability. The video is being recorded by Dr. Pallavi Upreti. The course coordinator and presenter for the video is Dr. Pallavi Upreti, affiliated to Department of Geography, Doon University. The academic expert and reviewer for the video is Professor Santosh Verma, Head of the Department, Department of Geography, SDM PG, Government Degree College, Doiwala, Dehradun, affiliated to Shri Dev Suman, Uttarakhand University. The video is produced and presented under the project name DTH Swayamprabha Channels of MHRD, New Delhi, India. Hello learners, I am Dr. Pallavi Upreti, Assistant Professor in the Department of Geography in Dr. Nityanand Himalayan Research and Study Center, Doon University, Dehradun. Today we are going to start with the module 4 of the climatology series, and in this particular module we will be discussing factors and aspects related to atmospheric humidity and stability and instability of the atmosphere. So let's begin. The main objective of this video is to understand what is humidity and how it is important in our atmosphere. What are the different types of humidity? What is the relation of humidity with heat and precipitation? And finally, we'll be understanding what is adiabatic process of cooling and heating of air parcel and what are the different conditions and temperatures associated with adiabatic processes. And finally, we'll be understanding what is atmospheric stability and instability and why it is important for various atmospheric conditions which exist globally. Our planet is made up of 71% of water, and the existence of this unique substance, that is water, first led to the evolution of life on our planet. Water is very, very unique. Why? Because it can exist as liquid, solid, and in form of water vapor or gaseous form. The existence of continuous water cycle on our planet helps in the distribution and redistribution of water vapors, of water and redistribution of heat on our planet to make it optimum for the sustenance of life. And one of the primary forms of water, as you can see, is water vapor. So how this water vapor is added in our atmosphere? The primary way in which the water vapor increases in the atmosphere is through evaporation, where due to excessive heating, the evaporation of liquid water takes place, which condenses in the form of clouds. And after condensing and reaching to a particular height, the precipitation takes place, which sends back the water to the Earth's surface. So through this water cycle, there is a continuous evaporation, condensation and precipitation of water, and water gets transformed into its various forms like liquid, solid and gaseous forms. So liquid water evaporates from oceans, lakes, rivers, plants and ground surface, and finally after reaching a point in the atmosphere it condenses in form of clouds and is sent back to the earth's surface. The atmospheric water vapor therefore represents the gaseous state of water, and in atmosphere the water vapor represents 2% of the total composition of the atmosphere. But this percentage is not uniform all over the globe. It varies both spatially and temporally, as it ranges from 0 to 5%. So it can be more over the tropical areas, over the equator, and can reduce drastically over the polar areas. So nearly 50% of the total atmospheric vapor is concentrated in the lower layers of the atmosphere up to the height of 2000 meters. And the presence of this water vapor in atmosphere is very essential factor for weather conditions of a particular region, and they may affect the overall global climatic and atmospheric conditions also. The presence of this water vapor in the atmosphere is called as humidity. So humidity is nothing but the amount of water vapor which is present in air. So if there is a lot of water vapor in the atmosphere, then the humidity will be definitely very high. So the higher the humidity, the wetter it feels outside. The more amount of water vapor will be present in the atmosphere, the more humid conditions it will lead to. So humidity in very simple definition is the amount of water vapor which is present in the air, which is added to the atmosphere through various biophysical processes, through water cycle and several atmospheric conditions. This presence of water vapor is very important. It is associated with several biophysical and thermal processes which exist and which are in continuous motion in our planet, like the amount and the form of precipitation, the surface temperature, the latent heat, the stability and instability of atmosphere, and several weather patterns and atmospheric condition can be associated with the presence of water vapor. The atmospheric humidity is also vital for climatic significance. Why? Because different forms of precipitation and several atmospheric conditions, weather patterns and atmospheric disturbances for that matter also depends upon the amount of humidity. It is also significant for the maintenance of overall heat budget of our planet, because it is this humidity only and it is through the existence of continuous water cycle which is present on our planet that the heat is redistributed to different latitudinal zones on our planet, making them optimal and maintaining the optimum average temperatures on Earth. Now, before moving on to further slides, we must understand one very important concept which is associated with humidity, which is latent heat. Latent heat, in very simple words, is the hidden amount of heat which is present in the water vapor. So, as we know that heat is spent during the time of evaporation, when the liquid water is converted into water vapor. But this heat during that process is not lost, and this heat is then released during the time of condensation, when the water vapor is converted into liquid or solid forms. So this particular heat which is released during the time of condensation is called as latent heat of condensation, and the role of this latent heat of condensation becomes very important when we discuss various concepts related to the instability and stability of the air parcel and the condensation of that air parcel leading to precipitation. So now we will look into other concepts of humidity and get back to this latent heat when we will discuss about the adiabatic processes and stability and instability of atmosphere. Now coming back to humidity again, first we have to understand what humidity capacity is. In very simple terms, humidity capacity can be understood as the moisture retaining capacity of air. So as we know that evaporation is the main mechanism through which water is converted into humidity or vapor. So naturally the areas which experience higher temperatures have higher rate of evaporation. The areas where the temperature is less, the rate of evaporation is also less. So the temperature shares positive correlation with humidity also. That is, the humidity capacity of an air parcel increases with increasing temperature and decreases with decreasing temperature. So humidity capacity is referred to as the capacity of any air parcel of certain volume at certain temperatures to hold moisture in it. So similarly, the humidity capacity becomes higher during the summer season and decreases during the winter months. And same goes for day and night also. It increases during the daytime and decreases during the nighttime. The extent of land and water and wind velocity also influence the humidity capacity of air to hold moisture. Oceanic and coastal areas also record high humidity capacity of air as compared to the remote continental areas. So humidity capacity decreases from equator towards the poles. Why? Because equatorial areas have more temperature as compared to the polar areas. And the humidity capacity is mostly expressed in grain per cubic foot or in gram per cubic centimeters or meters, as you can see in the diagram also. But the main important fact regarding humidity capacity is that it shares direct positive correlation with temperature. Coming to the types of humidity, the atmospheric humidity is expressed in number of ways. First is the absolute humidity, second is the specific humidity, and third one is the relative humidity. Now we will understand them one by one. The first one is the absolute humidity. Absolute humidity is the actual content of water vapor which is present in the atmosphere regardless of its temperature. So generally the absolute humidity is not affected with the increase or decrease of temperature if no additional water vapor is added through additional process of evaporation. But it changes with the contraction or expansion of air. So the absolute humidity decreases from equator towards the polar regions and from oceans towards the continental interiors. It is expressed as grams of water vapor present in per cubic meter volume of air. The total weight of moisture content per volume of air at definite temperature is therefore called as absolute humidity. So the higher amount of water vapor, the absolute humidity will definitely be higher in that particular parcel of air. So you can see in this particular diagram also the actual content of water vapor regardless of the air temperature. Now coming to the specific humidity, as absolute humidity talks about the actual content of water vapor which is present in the air regardless of its temperature, the specific humidity talks about the weight of the water vapor which is contained in a unit weight or amount of air, and it is generally expressed as grams of water vapor per kg of air. So the absolute humidity and specific humidity are, you can see that they are quite similar concepts. It is the mass of water vapor compared to the total mass of air parcel. So it represents the actual quantity of moisture in weights which is present in a definite air parcel. So as similar to the absolute humidity, the specific humidity is also very rarely affected by the changes in the air pressure or air temperature. Why? Because it is measured in the units of weights or grams. So it is directly proportional to the vapor pressure, which is the partial pressure exerted by the water vapor in the air, and therefore it is independent of other gases and it is inversely proportional to air pressure. So specific humidity decreases from equator towards the poles. It is therefore a measure of quantity of water that can be extracted from the atmosphere as precipitation. So this is the specific humidity. The third type of humidity is the relative humidity. It is the most common used measure of humidity, and it is defined as the ratio of the amount of water vapor actually present in the air having definite volume and temperature, and it is generally expressed in terms of percentages. It is the amount of water in the air relative to the saturation amount of the air which it can hold at a given temperature multiplied by 100. So in other words, the relative humidity is the absolute humidity divided by the humidity capacity into 100 or multiplied by 100. Why? Because it is expressed in percentage form. So the relative humidity is proportion of the absolute humidity of an air of a definite volume at a given temperature to the humidity capacity of that air. And there is an inverse relationship between the relative humidity and temperature, which means that if the temperature increases, the relative humidity decreases, and if the temperature decreases, the relative humidity increases. So there is an inverse relationship between temperature and relative humidity. It is important to note that when the humidity capacity and absolute humidity of the air are the same, the air is said to be saturated and the relative humidity becomes 100%. So the relative humidity of any region is definitely affected by these two variables, that is the absolute humidity. So if the absolute humidity of any region increases or decreases, it affects the relative humidity. And second, if the temperature of the air decreases so that the humidity capacity also decreases, it also affects the relative humidity. As you can see in this particular diagram also, as the temperature increases, 10 degrees Celsius here, 20 degrees Celsius here, 30 degrees Celsius here, the humidity capacity also increases. So as the humidity capacity increases, there is a change in the relative humidity also. Here the relative humidity is 100%. Here the humidity capacity increases, so the relative humidity decreases. And here the relative humidity further decreases because of the increase in temperature, the humidity capacity has increased further. Relative humidity shares inverse relationship with temperature. Now, relative humidity has great environmental significance. Why? Because relative humidity affects the climate significantly because of the possibility of precipitation depends on it. High and low relative humidity is indicative of the possibility of wet precipitation and dry condition respectively, which may prevail in any particular area. So the amount of evaporation also depends on the relative humidity. Evaporation decreases with the high relative humidity while it increases with the low relative humidity. Now relative humidity is also directly related to human health and comfort also. Very high relative humidity, as you can see in this particular area, very high relative humidity is injurious and very uncomfortable to human health also. This is why the equatorial areas with very high temperatures and very high relative humidity and tropical areas with hot deserts with very low relative humidity are unfavorable for human health. Relative humidity therefore also affects the human beings and it is associated with their comfort also. So it has to be in a comfortable range. Very low and very high relative humidity is definitely very uncomfortable for human beings. So humidity is closely associated with heat also. Why? Because humidity can make a hot day feel even hotter, because in general when the sweat evaporate it gives you a cooling effect, but when the air contains as much as water vapor as it can hold, that means when the relative humidity is very high, what happens? The water condenses onto your skin just as fast as it evaporates, giving you a very sticky, uncomfortable feel, providing no cooling benefits, therefore making a hot day feel even more hotter. So humidity, very high humidity is closely associated with the uncomfortable and unhealthy environment which exists. Atmospheric stability and instability. So what do you mean by the word stable? It means that something which is unlikely to change, or something which remains in constant state of balance. The opposite is true for something which is unstable, which means that either that thing is continuously in mobile state, or it changes position, either it falls or it rises upwards. So it is unstable condition. So similarly, these concepts, when they are applied to the motions of air parcels in the atmosphere, it leads to atmospheric stability or instability. So stability is the condition in the atmosphere which is in state of complete equilibrium. That is, there is no movement of air, while the instability is associated with the vertical movement of air parcel in the atmosphere. So the topic of stability and instability in atmospheric sciences is very, very important. Why? Because it is closely associated with the formation of clouds, with the type and form of precipitation, and therefore, it is closely related to the stable conditions in the atmosphere and unstable conditions in the atmosphere. So while discussing the atmospheric stability and instability in atmospheric sciences, we typically consider air parcel to be imaginary blobs or globules of air that can expand or contract freely but do not mix with the air around them or break apart. So this particular parcel of air can either expand or contract due to its vertical ascent or its descent respectively. Here it is also important to note that the movement of air parcel in the atmosphere and the associated temperature change can be called as adiabatic process, wherein the temperature of this air parcel changes due to the changes in its air pressure, which are primarily induced because of its vertical movement. So the air parcel either ascends or descends, and the consequent changes in the temperature without external gain or loss of heat is called as adiabatic change of temperature. So in this particular diagram, as you can see, that when the air parcel ascends, less and less of atmospheric pressure is applied on this air parcel, which leads to its expansion while ascending upward, and consequently this particular parcel of air cools down. But this adiabatic process is also a reversible process. Why? Because when the parcel of air descends, due to the increase in the atmospheric air pressure on that air parcel, it consequently contracts and warms up. So any ascending parcel of air will definitely expand and becomes cooler, and any descending parcel of air will contract and become warmer. So this change in temperature with the vertical ascent and descent of air parcel without externally mixing up with the outer air is called as adiabatic process. So there is no exchange of heat involved in the adiabatic process, and the adiabatic process is reversible. That is, it can lead to expansion of the air parcel, and on the other hand, it can also lead to its contraction. So the stability of air also depends upon the distribution of temperature at various altitudes in the atmosphere. As we have talked in numerous earlier slides, that the temperature in the troposphere decreases with increasing height at a rate of 6.5 degree per thousand meter, which is also called as normal lapse rate, because this is the normal decreasing rate of temperature which exists in the troposphere, and it is also called as the environmental lapse rate, because generally at this rate in the environment the temperature decreases with increasing height. So this lapse rate may vary substantially. Why? Because this is the average rate, so it may be higher at certain points and it may be lower at certain points. So it varies from place to place and time to time, and this particular variation in normal lapse rate immensely influences the atmospheric stability. The variation in normal lapse rate influences the environment around the ascending or descending parcel of air, which leads to instability or stability conditions in the atmosphere. So, while the parcel of air is ascending adiabatically, there is a change in its temperature. There is no exchange of heat which is taking place between the parcel of air and the outer environment. But definitely, if the temperature of the outer environment, the normal lapse rate fluctuates, it impacts the cooling and heating of that air parcel. There is no exchange of heat, but the cooling and heating of that air parcel is definitely affected by it. So the normal lapse rate and variations in normal lapse rate influences the stability and instability conditions in the atmosphere. So adiabatic cooling and heating of the air parcel is associated with the ascent and descent of the air parcel. An ascending parcel of air at a given volume and temperature expands as pressure decreases and cools down. Similarly, a descending parcel of air contracts and thus its volume decreases but temperature increases. The decrease or increase in temperature due to ascent or descent of air without addition or subtraction of heat from the outside environment is called as adiabatic change of temperature. So this change in temperature of air parcel is related to the changes of pressure without external gain or loss of heat. So this is called as the adiabatic process. So suppose the temperature of this particular parcel of air at the ground was 32 degrees Celsius, and when it rises up, the temperature of this parcel decreases while it expands, because less and less of atmospheric pressure is applied over this air parcel as it moves up in the troposphere. So at 3000 meters of height, this parcel of air has expanded and the temperature of this parcel has reduced. Same process is applied when this particular parcel of air is coming down. So when it comes down, the sinking parcel of air is compressed and the temperature of this parcel of air again increases. So there is increase and decrease in the temperature of this parcel of air without any addition of external heat from the outside environment. So this is called as adiabatic process. So adiabatic process is basically of two types. There is adiabatic cooling of air and there is adiabatic warming of air. So adiabatic cooling of air basically takes place when, due to some initial force, the air at the ground surface is lifted. So as it lifts, the environmental air pressure outside the air parcel decreases. The air molecule inside the parcel definitely start pushing towards the outer wall of this particular air parcel and expands adiabatically. So in this process, the energy in this particular parcel of air is also utilized, and therefore the internal temperature of this parcel decreases on moving up. So to summarize, the rising air parcel expands and cools down adiabatically without exchanging heat from the outside environment. Besides this, you have adiabatic warming of air. Now, in this particular case, what happens? You have to imagine that there is a sinking parcel of air which is moving back to the Earth's surface. So, the air parcel is moving into an environment with high pressure. So, as it comes down, more and more outside air pressure is applied on this particular air parcel. The higher environmental pressure pushes against the walls of the parcel, causing them to compress and raise the inside temperature. The process is adiabatic heating. So again, no heat is exchanged with the environment, but the temperature increases of this parcel of air. However, temperature change in this parcel can still occur, but without mixing of air. So to summarize, the descending parcel of air warms up adiabatically without exchanging heat from the outer environment. The adiabatic change of temperature is primarily of two types. First one is the tri-adiabatic change of temperature. So we know generally that the existing average normal lapse rate is 6.5 degrees Celsius per 1000 meters, which exists in our environment normally. But when the temperature of unsaturated ascending partial of air decreases at the rate of 10 degrees Celsius per 1000 meter, with increasing height, it is called as dry adiabatic lapse rate. So the temperature in the ascending parcel of air decreases at much higher rate as compared to the existing environmental lapse rate. So you can see in this diagram also that in general, the temperature decreases with increasing height at the rate of 6.5 degrees Celsius per 1000 meter. But despite of this existing normal lapse rate, the temperature in the unsaturated ascending parcel of air decreases at much higher rate, which is called as dry adiabatic lapse rate. So you can see that near the ground surface, it is somewhere around 32 degrees Celsius. And as it moves 1000 meters up this particular air parcel, the temperature decreases to 22 degrees Celsius. And it continuously decreases with increasing height until it has not reached its condensation level. So the dry adiabatic lapse rate is more than the normal lapse rate, which is on an average 10 degrees Celsius per 1000 meters. The second type of adiabatic change of temperature is wet adiabatic change of temperature or wet adiabatic lapse rate. So when the already ascending parcel of air keeps on ascending beyond the condensation level, the rate is lowered due to the addition of latent heat of condensation to the air, and now the air parcel decreases at moist adiabatic lapse rate, which is 6 degrees Celsius per 1000 meter instead of dry adiabatic lapse rate. So you can see in this particular diagram, this particular parcel of air was initially lifted due to some external force, and the temperature in this particular parcel of air initially decreases at dry adiabatic lapse rate, which is approximately somewhere around 10 degrees Celsius per 1000 meter. But after reaching its level of condensation, the condensation takes place. So when the condensation takes place in this particular parcel of air, the latent heat of condensation is released and added to this particular parcel of air, which increases the overall temperature of this particular parcel of air, and it becomes unstable. And now this particular parcel of air, after the release of latent heat of condensation and addition of latent heat of condensation to this air parcel, the temperature of this air parcel decreases at much lower rate, which is 6 degrees Celsius per 1000 meter, and this is called as the moist adiabatic lapse rate. So we have two types of adiabatic lapse rate. We have the dry adiabatic lapse rate, wherein the temperature of the air parcel decreases with increasing height at 10 degrees Celsius per 1000 meters rate. And then we have the moist adiabatic lapse rate or wet adiabatic lapse rate, wherein the temperature of the ascending parcel of air decreases at much lower rate, which is 6 degrees Celsius per 1000 meters on moving up. The adiabatic process and the consequent temperature changes in the parcel of air can be understood with this particular diagram also, wherein you can see that initially the temperature of this rising parcel of air decreases at dry adiabatic lapse rate, which is 10 degrees Celsius per 1000 meter, which means that while this parcel of air moves 1000 meters up altitudinally, the temperature of this rising parcel of air decreases 10 degrees Celsius every 1000 meters. So initially consider that the temperature at the ground surface of this rising parcel of air was 20 degrees Celsius. So on moving every 1000 meters, the temperature decreases at 10 degrees Celsius till the point where this particular rising parcel of air has not achieved the condensation level. Once it achieves the condensation level, the latent heat of of condensation is applied to this air parcel again, which increases the temperature of this parcel. So now the temperature of this ascending parcel of air, instead of decreasing at dry adiabatic lapse rate, start decreasing at wet adiabatic lapse rate, wherein because of the addition of the excess latent heat of condensation to this air parcel and the consequent increase in the temperature of this air parcel, the decrease in temperature of this air parcel is much more lesser as compared to the initial rate, which was 10 degrees Celsius per 1000 meter. So now this parcel of air decreases at the rate of wet adiabatic lapse rate, which is 6 degrees Celsius per 1000 meters. So at 4000 meters, the temperature will become 2 minus 6 degrees Celsius, which is minus 4 degrees Celsius. And on further ascending, it becomes minus 10 degrees Celsius. So now it is decreasing at a much lesser rate after reaching the condensation level. So the adiabatic process and consequent changes in the temperature is the manifestation of the interplay between the normal lapse rate, existing environmental lapse rate, and the dry adiabatic lapse rate and wet adiabatic lapse rate, which leads to the stability and instability in the atmosphere. So the atmospheric stability and instability is directly associated with the vertical movement of air, while the air with no vertical movement is considered as stable. The vertical movement leads to instability of air. An ascending air mass becomes unstable and becomes warmer than the surrounding air mass, while descending air mass becomes stable. The stability and instability depends upon the relationship between normal lapse rate and adiabatic change of temperature. While adiabatic rate is always constant, so you have to understand that the adiabatic change of temperature, whether it is the dry adiabatic lapse rate or wet adiabatic lapse rate, they are more or less constant because they are associated with the vertical ascent of that air parcel and the pressure conditions inside that air parcel. However, the normal lapse rate, although the average normal lapse rate is 6.5 degrees Celsius per 1000 meters, but this normal lapse rate may vary from place to place, leading to instability and stability in the atmosphere. Several atmospheric phenomena also depend upon the stability and instability of atmosphere, like the formation of clouds and the precipitation, and type and forms of precipitation also depends upon the instability and stability conditions of the atmosphere. Now let's discuss atmospheric stability first. What is atmospheric stability? Atmospheric stability represents the condition of absence or restriction of vertical motion in the atmosphere when the normal lapse rate is lower than the dry adiabatic lapse rate of an ascending dry air parcel, and if it is not saturated and attain a dew point, it becomes colder than the surrounding environment at certain heights, and it becomes heavier and it starts descending, leading to anticyclonic or stable conditions in the atmosphere. So you can understand this stability with this example. If the temperature of the parcel of air near to the ground surface is 20 degrees Celsius and the temperature of the surrounding environment is also 20 degrees Celsius. So what happens now is that due to some initial momentum, when this parcel of air starts rising, the temperature of this parcel of air decreases at dry adiabatic lapse rate, which is 10 degrees Celsius per 1000 meter. But the temperature of the surrounding environment decreases according to the normal lapse rate, which is 6.5 degrees Celsius per 1000 meter. So at the height of 1000 meters or 1 kilometer above the surface of Earth, what happens? This parcel of air is rising and the temperature of this parcel of air at this particular height becomes 10 degrees Celsius, while the temperature of the surrounding environment becomes 13.5 degrees Celsius. So at this point, if the condensation does not happen in this parcel of air, you can see that the temperature of this parcel of air is less than the surrounding environment. Okay, so you can see that at 1000 meters the temperature of the surrounding environment is 13.5 degrees Celsius and the temperature of this parcel of air is 10 degrees Celsius. So definitely the temperature of this ascending parcel of air is less than the surrounding environment. So what happens, since this parcel of air becomes colder than the surrounding air, it becomes heavier and it starts descending, leading to stability. Why? Because now the vertical circulation or vertical movement is retarded, leading to stable atmospheric conditions. So this process causes stability of atmospheric circulation, due to which the vertical circulation of air is restricted, leading to atmospheric stability in these regions. And such ascending air is called to be in state of equilibrium. Now what happens, sometimes the normal lapse rate in certain layers of the atmosphere is exceptionally low, which is somewhere around 4.6 degrees Celsius per 1000 meters. So at these stages, the normal lapse rate is even lower than the wet adiabatic lapse rate, which is 6 degrees Celsius per 1000 meters. So in such conditions, what happens, that if the normal lapse rate is even lesser than the wet adiabatic lapse rate, even at condensation point, the further vertical motion of the air is completely stopped. Thus, the air is said to be in absolute stable condition, and such atmospheric condition is called as absolute atmospheric stability. So here in this diagram, you can see the conditions of absolute stability where exceptionally low environmental lapse rate exists. Here in this case, it is somewhere around 5 degrees Celsius per 1000 meters. So because of this exceptionally low environmental lapse rate, which is lesser than the wet adiabatic lapse rate, also the vertical movement of air is completely stopped, leading to the absolute stability or absolute atmospheric stability conditions. So these types of conditions are best represented opposite to the normal lapse rate conditions, which happens in the case of temperature inversion. So temperature inversion is a situation where the conditions of absolute atmospheric stability occur most commonly in the atmosphere. Now coming to the atmospheric instability, when the normal lapse rate is greater than the triadiabatic lapse rate of ascending parcel of air, the rising air continue to rise upwards and expand and is in unstable equilibrium. Such condition leads to atmospheric instability where the air parcel continuously remains in state of mobility and it keeps on ascending. So in other words, the atmospheric instability is caused when the rate of cooling of rising air, that is dry adiabatic lapse rate, is lower than the normal lapse rate. So let's understand atmospheric instability with this particular example. So if the temperature of the certain parcel of air at the ground surface is considered to be 40 degrees Celsius and the temperature of the surrounding environment is also considered to be 40 degrees Celsius, so the temperature in air parcel decreases at dry adiabatic lapse rate initially, which is 10 degrees Celsius per 1000 meters. And if the existing normal lapse rate is suppose 11 degrees Celsius per 1000 meters, the normal lapse rate is very high, more than the dry adiabatic lapse rate. Also, what happened in this case, when you reach 1000 meters of height, the temperature of the surrounding environment becomes 29 degrees Celsius, while the temperature of this ascending parcel of air becomes 30 degrees Celsius. So the temperature of this ascending parcel of air is more than the surrounding environment, which further forces the air to move upwards. So the rising air, being warmer than the surrounding air, continue to rise and expand to cause atmospheric instability. So because it is warmer than the surrounding environment, it still remains unstable and continue to rise. So such conditions existing in the atmosphere are called as atmospheric instability. So what happens in the atmosphere after ascending to a particular limit when the ascending parcel of air reaches particular height, when the temperature of this parcel of air is equal to the normal lapse rate. So this parcel of air has equal temperature to the surrounding environment. So at that point what happens? The further upward movement is stopped. Such air is said to be in state of neutral equilibrium. The instability conditions can be very much seen in this picture where you can see a cumulonimbus cloud rises and expands over Africa as a product of instability within the atmosphere. So definitely the normal lapse rate or the environmental lapse rate in the surrounding areas of this air parcel would have been very, very high, which would have forced this parcel of air to rise to these vertical extents. And sometimes these type of conditions may also lead to absolute instability also, wherein the air remains very, very unstable and continue to rise, leading to conditions of absolute instability in these regions. But sometimes what happens when the ascending parcel of air reaches height that the temperature of this parcel of air is equal to the normal lapse rate, what happened? Its further upward movement is stopped, leading to neutral equilibrium conditions also in such areas. So absolute instability represents the conditions where the air parcel is in continuous state of vertical movement, where it continuously ascends because of exceptionally high surrounding environmental lapse rate, and it keeps on rising till its temperature is not equal to that of the surrounding environment. So what happens if the normal lapse rate is very, very high? The temperature of the surrounding environment remains low as compared to the ascending air parcel. So as the ascending air parcel is warmer than the surrounding environment, it continue to rise till the point it is not able to match up that environmental lapse rate or environmental temperature. So such state of continued upward movement of air is called as absolute instability. But for absolute instability to happen, the normal lapse rate should be very, very high. Then the dry adiabatic lapse rate also, and definitely it will be higher than the wet adiabatic lapse rate also. So when the normal lapse rate is higher than both wet adiabatic lapse rate and dry adiabatic lapse rate, the absolute instability conditions occur in the environment. Now coming to mechanical instability. Sometimes abnormal conditions prevail when the normal lapse rate, especially in the upper layers of the troposphere, is exceptionally very high. So the rate of decrease of temperature in these particular layers is somewhere around 20 degrees Celsius to 35 degrees Celsius per 1000 meters, which means that there is a very immense or rapid decline of temperature in these particular layers. In such conditions, the upper layer of the atmosphere becomes exceptionally cold and dense than the underlying layer of the atmosphere. In such extraordinary conditions, there is an automatic overturning of the air without any initial trigger, and the cold and dense upper air automatically starts descending. This kind of situation represents mechanical instability and is often associated with upper air temperature inversion also. So such conditions contribute to the formation of most violent storms and tornadoes because there is a sudden decline in the temperature conditions leading to extensive massive changes in the pressure conditions of the surrounding area, leading to turbulent and most violent storm and tornado-like conditions in the areas. Now coming to conditional instability, a more frequent type of atmospheric instability is known as conditional instability. This occurs due to specific conditions in the atmosphere, which is that the environmental lapse rate is between the dry adiabatic and wet adiabatic lapse rate. So if the wet adiabatic lapse rate is 6 degrees Celsius per 1000 meters and the dry adiabatic lapse rate is 10 degrees Celsius per 1000 meters, so the existing normal lapse rate or environmental lapse rate will somewhere between these two lapse rates. It simply means that the atmosphere is stable with respect to unsaturated parcel of air, but unstable in relation to the saturated parcel of air. The air is stable in the lower layers of the atmosphere, but if it is forced to rise due to some specific initial momentum like heating or orographic barrier or convergence until the level of condensation. So at this level, the rising parcel of air becomes warmer than its surrounding air and is free to rise. The state of a layer of unsaturated air when its lapse rate of temperature is less than the dry adiabatic lapse rate, but it is greater than the moist adiabatic lapse rate is called as conditional instability. Let's understand conditional instability with the help of this example. Consider the temperature of the parcel of air near to the surface of Earth to be 40 degrees Celsius. So because of any initial momentum, this particular parcel of air is forced to rise up. And initially the temperature in this particular rising parcel of air decreases at the rate of 10 degrees Celsius per 1000 meter. But because of existing environmental lapse rate, which is 8 degrees Celsius per 1000 meters, for example, if the environmental lapse rate is 8 degrees Celsius per 1000 meters, so in these conditions, you can see that the environmental or existing environmental lapse rate is less than the dry adiabatic lapse rate, but it is more than the wet adiabatic lapse rate. So there are specific conditions existing in the atmosphere now. So what happened at 1000 meters, you can see that the temperature of the surrounding environment is 40 degrees Celsius minus 8 degrees Celsius, which is 32 degrees Celsius. And at 2000 meters, the temperature of the surrounding environment becomes 24 degrees Celsius. But the temperature of this ascending parcel of air at 2000 meters become 20 degrees Celsius because each 1000 meter the temperature is decreasing by 10 degrees Celsius. So at 2000 meters, what happened? This particular rising parcel of air is 4 degrees cooler than the surrounding environment. You can see here 20 degrees temperature is of this rising parcel of air and the temperature of the surrounding environment is 24 degrees Celsius. So the temperature of the surrounding environment is more than the rising parcel of air. So therefore, you can see that the rising parcel of air becomes colder than the surrounding environment and leads to stability. However, if at this particular point condensation takes place, what happens? The latent heat of condensation is applied to this parcel of air. And as soon as the latent heat of condensation is applied to this parcel of air, this parcel of air becomes unstable and continue to ascend upwards under the wet adiabatic lapse rate. So here onwards, the decrease in temperature of this air parcel is at 6 degrees Celsius per 1000 meters. So what happens now? At 4000 meters, the temperature of the surrounding environment is 8 degrees Celsius and the temperature of this ascending parcel of air has also become 8 degrees Celsius. Why? Because 20 degrees Celsius minus 6 degrees Celsius, 14 degrees Celsius, further minus 6 degrees Celsius is 8 degrees Celsius. And if you move further 1000 meters up also, at 5000 meters, the temperature of the surrounding environment becomes 0 degrees Celsius. But the temperature of this parcel of air becomes 2 degrees Celsius. 8 degrees Celsius further minus 6 degrees Celsius is 2 degrees Celsius. So at this point, you can see that the temperature of this rising parcel of air is more than the surrounding temperature, which makes this parcel unstable, forcing it to ascend further. And as the parcel of air ascends, you can see that the temperature difference between the rising parcel of air and existing surrounding environmental temperature, it keeps on increasing. Here at 6,000 meters, the rising air is 4 degrees warmer than the surrounding environment. So because of which the rising air becomes unstable and instability conditions prevail in this part of the atmosphere. So it is clearly evident that under conditional instability, because the environmental lapse rate is between the dry adiabatic lapse rate, it is less than the dry adiabatic lapse rate and it is more than the wet adiabatic lapse rate, conditions exist which leads to unstable conditions as well as stable conditions in the atmosphere. While the environmental lapse rate is stable for the dry rising unsaturated parcel of air, environmental lapse rate is unstable for the saturated parcel of air, leading to conditional instability. So summarizing the video now, humidity is the amount of water vapor which is present in the atmosphere. Humidity capacity is the moisture retaining capacity of the air. And this humidity can be expressed in number of ways. It can be absolute humidity, specific humidity, and relative humidity. And humidity in the atmosphere is closely associated with the adiabatic change of temperature also, which means the change in temperature of the parcel of air which is induced because of its vertical motion and without exchange of any heat from the outer environment. And this adiabatic change of temperature can be expressed as dry adiabatic change of temperature, DALR, dry adiabatic lapse rate, wherein the temperature of the parcel of air decreases at the rate of 10 degrees Celsius per 1000 meters, and wet adiabatic lapse rate, wherein the temperature of the ascending parcel of air decreases at the rate of 6 degrees Celsius per 1000 meters approximately. And it is greatly related to the instability and stability of the atmosphere. The relationship of dry adiabatic lapse rate and wet adiabatic lapse rate along with the existing normal lapse rate defines the stability and instability in the atmosphere. When the normal lapse rate is lower than the dry adiabatic lapse rate, it leads to stability. While if the normal lapse rate is greater than the dry adiabatic lapse rate, it leads to instability conditions. So humidity in air influences several biophysical thermal processes on Earth and existing atmospheric conditions, including the stability and instability of our atmosphere. And it also influences the general weather patterns existing in different regions of the world. So it influences the cloud formation, precipitation, formation of fogs, different types of rainfall, and different forms of precipitation also. And all these things we are going to cover in this particular module in the coming videos. So I hope this video was informative. Thank you so much.